less than 3.3 complex numbers, standard MA912.NSO.2.1. Pure imaginary numbers are values that are basically what they are, imaginary. They don't exist. Sometimes we need to be able to take solutions. So mathematicians decided to define imaginary numbers. Imaginary numbers, which we use the letter I, is what we use for the square root of -1. So we say that I is the square root of -1 and I squared is -1. So like we look at the numbers of the form 6i, -2i, and I radical 3, they're all called pure imaginary numbers because of a specific thing. Pure imaginary numbers have the form of bi. B is the real number, and I, radical -1, is your imaginary value. Some properties that we need to have are known as the associative and commutative properties of multiplication. They hold true for pure imaginary numbers. So then we have some values that we need to know that make things sense. If we see I to the power of just plain I, that's representing I. I squared is -1. I cubed is basically saying I squared times I, or negative I. And then if we see also I to the 4th power, that is saying I squared times I squared. So -1 times the -1 is a +1. With those 4 pieces, then you can define what value of I to any power is for it. In example 1, they want us to take the square root of negative numbers. So they say square root of -294. What they did is they separated your -1 out and then wrote 294 as 7 squared times 6. The reason they did 7 squared is because that's 49. I can take the square root of 49 to become +7. So there's my 7i with the square root of 6 that did not come out, leaving me with 7i radical 6. We're going to try one with their check problems. On the check problem, it says square root of -75. So square root of -75, you rewrite it as square root of -1 times the square root of 25 times the square root of 3, because 25 times 3 is 75. So now we break it down further. We can take the square root of -1 is the letter I. We can take the square root of 25, that is plain 5, and 3 is still in the bucket. And then we just rewrite it to say 5i square root of 3, which is letter C. In example 2, it talks about pure imaginary products, the multiplication of pieces. So when we look at our piece, it says simplify square root of -10 times the square root of -15. So what they did is they isolated out the negative I piece. So they rewrote it as I with a square root of 10. Then the I squares, that's where they multiplied together. I squared becomes your -1. They multiplied 10 times 15 and got their 150. And then they took 150, think of it as $1.50. So there's 25 quarter represented by 25 cents. There's 6 quarters in $1.50. And then they broke out the 25, which becomes -5 radical 6. But we're going to try the problem that says the check. In the check, it says square root of -16 times the square root of -25. So square root of -16 times the square root of -25. I'm writing it out as, think of it as I with a square root of 16, I with a square root of 25. Because remember, I represents square root of -1, and all I did was isolate that square root out. So I become 4i times 5i. That is 20i squared. Well, remember, I squared is -1. So then we see 20 times -1, so your answer is -20. In example 3, it says equation with pure imaginary solutions. It says solve x squared plus 81 equal to 0. So you start with your original problem, and then we're going to subtract 81 over. We're going to subtract 81 over, so it now becomes -81. Then it says take the square root of each side. So we're now seeing x squared equals -81. We are taking the square root of both sides. When you take the square root of x squared, it just becomes x. Square root of negative 81, think of it as I with a square root of 81. It's going to be a plus minus situation. So now I see x equals plus and minus I with a 9. So I see 9I, so 9I. We look at our check problem. It says 3x squared plus 27 equals 0. So we start out with our original problem. First thing I'm going to do is I'm going to divide, I'm subtracting the 27 over. So we now become 3x squared equals negative 27. Then I'm going to divide by 3 to both sides. So I get x squared equals negative 9. Now we're going to take the square root of both sides. When you take the square root of both sides, that causes a plus minus situation to happen. Well, you're saying the square root of negative 9, so that's I with a 3. So we have 3I and negative. 3I because there's a plus minus, there is a plus minus situation happening. Complex numbers. Complex numbers is any number that can be written in the form of a plus bi. In this instance, the a and b are the real values, and I is your imaginary value. We call a the real part, and bi is the imaginary part. So when we look at our Venn diagram piece here, so the Venn diagram shows the set of complex numbers. Notice that all the real numbers are part of the set of complex numbers. So we have real numbers and we have imaginaries. So notice the letters. Q represents rational numbers. The I is your irrationals. Z represents our integers. Remember, those are your positive and negative whole numbers. W is just the whole numbers, no negatives, and N is our naturals starting at 1. And then you have your imaginary parts where B cannot be 0. So you have your pure imaginary values where A is not 0. So two complex numbers are equal if and only if their real parts are equal to their imaginary parts are equal. What we have here is our properties. So to add and subtract complex numbers, we're going to combine like terms. So what does that mean? You're going to combine the real parts, and then you're going to combine the imaginary parts. Two complex numbers are known in the form of a plus bi and a minus bi. These are called complex conjugates. They should be opposite in sign. The reason I call them complex conjugates and conjugates is because they are part of difference of squares. In the form of a squared minus b squared formula, which becomes a plus bi times a minus b. So a radical equation expression is in the simplest form if no radicals contain the fractions and no radicals appear in the denominator. So if you get a complex conjugate, to simplify a fraction of a complex number in the denominator, we are calling it rationalizing the denominator. So we'll see some problems like that. In example 5, it says add or subtract the complex numbers. So they started out with 8 plus 3i minus sign 4 minus 10i. So what they did is they're going to you're grouping our real pieces together by the commutative and associative properties. So I see an 8, it's a whole number. I see a 4, so I'm writing 8 minus 4, because remember, there's a minus sign between them. Plus, then it's the 3i. So what I did is the 3 piece, because there's my I on the outside. Now it's a minus 10. So I'm going to write a negative 10 inside here to cause the minus situation. So now I see 8 minus 4 is 4. 3 minus the minus means plus. And that's where we get our 13 from. When we look at our check problem here, it says -5 plus 5i minus a minus. So remember, there's a minus sign. So I'm saying -5 minus a -3 plus 5 minus an 8 with an I. And now we see -5 plus 3 plus 5 minus 8 is a -3 with an I. So we get -2 minus 3i. So -2 minus a 3i in our piece. In example 6, it's talking about multiplying complex numbers. So it says the voltage of an AC circuit can be found using the formula, and they give you a formula that they want you to use. And it says it's V is CI, where C is the current and I is the impedance. So it tells you that C is 3 plus 2J amps, and I is 7 minus 5J ohms. So we need to determine our voltage. So remember, they gave you a formula that says V times CI. V is equal to CI. So what they did is we wrote 3 plus 2I times C minus 5J. So now they're using the FOIL method for this problem. You can use the box method. It's your choice. So what they're doing is they did first times the first. So 3 times your 7, then 3 times your 5J. Then 2J times your 7, and then 2J times your -5J again. We ended up with 21 in the first bubble, and then there's our -15J. We get 14J in the sequence, and then -10J squared. So we're going to combine our like terms. So we have 21 minus the -1J. We have a 1J here. And then it's -10, remember, and then J squared, there's your -1. So we're getting actually 21 minus a -10, so it's 21 plus 10, giving you 31 minus J. The other way that you can do this is your box method. So this is actually 31 minus J volts. So if you had done the box method to do your multiplication, you would have had your 3 and then 2J up top, 7, and then your -5J on the bottom. And then you would have just multiplied corner to corner. So this is where you get the 21, the 14J, the -15J, and then the -10J squared. And then you would have brought everything out, which would have given you your 21 minus J minus 10J squared. So again, this is your -1, so you would have seen 21 minus J minus 10 times the -1, which is 21 minus J plus 10, and there's your 31 minus J again. In sample 7, it's about dividing complex numbers. What that means is, so they give us a problem that says 5i divided by 3 plus 2i. So we need to rationalize the denominator. In order to rationalize the denominator, you must multiply the denominator and numerator by the conjugate of the denominator. So what they did is they started out with 5i over 3 plus 2i, and they multiplied the numerator and denominator by 3 minus 2i twice. And so then you do each piece individually. You do your numerator multiplication, and then you do denominator multiplication. And that's where they got the 15i minus 10i squared over 9 minus 4i squared. And then apply the rules that I squared is -1. So that's where they got 15i minus 10 times the -1. And the bottom, 9 minus 4 times -1. and resulted in 15i plus 10 over 13. And then notice it because it needs to be in simplified form. The a plus bi form is where you split each piece, but we're going to try it with our own problem. So in this problem, it says 2i over negative 4 plus 3i. So we're going to write 2i over negative 4 plus 3i times negative 4 minus 3i. The sign at the beginning does not change. It's the sign in the middle. That is where it happens. So now what we're going to do is we're going to work on the numerator only and then the denominator. So in the numerator, we have 2i times negative 4 minus 3i. I'm using distributive property to multiply in. So I get negative 8i minus 6i squared. Remember, I squared is negative 1. So it's negative I minus 6 times negative 1, which is negative I plus 6. But because it needs to be in the order of a plus bi, I'm going to write 8 is second. So it's 6, positive 6 minus 8i. Now we're going to look at our denominator. In the denominator, we have negative 4 plus 3i times negative 4 minus 3i. The general formula we're going to use is called a squared minus b squared. A is negative 4 and b is a 3. Don't worry about it being positive or negative, just it's a 3. So now we're going to plug in to our bubbles. So I'm saying negative 4 squared minus 3 squared with an I squared. So we get 16 minus 9 times a negative 1. So it's 16 plus 9, which is 25. So we're at this point, and then we separate our pieces. So we get 6 over 25 minus 8 over 25 with an I.